1 second here. Okay, hopefully everyone can see the screen. All right, so thank you very much. Thank you, Alexius, and thank you, Salvador, for inviting me to present today. I just want to let those of you who English is your second language, I'll try and speak as slowly and enunciate as well as I can, but understand that if you have any questions or if I go too fast or I get too excited and go over things that you may have questions on, please feel free to ask them at the end of this presentation. Also, I hope everyone is safe, and we're coming up on the year anniversary of the pandemic lockdown. So hopefully we will move into the next few months where it starts opening up more, and I wish everyone well and safe. So the purpose of this presentation is to go over work that we've done at MDRU with the University of British Columbia in our research group, as well as the work that I did as part of the CIMIC Footprint project. So I just need to acknowledge a lot of my colleagues and the students who worked on this project. And much of what will be presented throughout the hour is work that was done, research by these various individuals, and the great work that was done by the students Guillaume Lesage and Kevin Byrne at the University of Alberta, and the recent publications that we've just had with Alain Plouffe of the Geological Survey of Canada and Travis Furby. And I just want to acknowledge the late Peter Winterburn, who was a researcher at MDRU, who is unfortunately no longer with us, and so a lot of the work is dedicated to his memory. So porphyry copper deposits are large-scale systems, and they the exploration for these is an ongoing research topic, not just in an academic sense, but in an industry as well. And my colleague Farhad Bazari likes to put this short little abstract of the work done by Gustafson and Hunt in the mid-1970s at the porphyry copper deposit at El Salvador, Chile, which is where I was fortunate enough to do my PhD work some time ago. But the key point about this little abstract is that the discovery of the porphyry copper deposit at El Salvador was based on the fact that the geologists who were going out there and doing the exploration work, doing the boots on the ground, as it were, observed these glassy quartz veinlets in the gravels and followed this up the ore leading to the Turquoise Gulch, which eventually led to the discovery of the large ore body that's been mined in the past and up to current times. But the key feature of this is that the geologists were able to make the key observations that noted that there is something different or anomalous about these gravels, and that it led to the discovery. And there are many, many different techniques and tools and focuses that we use as exploration geologists, but it's identifying these key anomalous features that leads to and hopefully culminates in the discovery of a large-scale system. And why that is important is that porphyry copper deposits are found throughout the world. We have fairly good models and understanding of how and where these deposits occur, and some of them are small, some of them are large. But the main issue as we move into the next century of discoveries is that a lot of these deposits are at surface or near surface. And the importance of new discoveries as we move forward is how do we find these at depth, or how do we recognize deposits that may not necessarily have been economic in the past, but have features that we want to explore for and pursue today, or target today, or bring into our new exploration programs. And the tectonic setting of where these specific deposits are located, particularly in North America and South America on the Cordillera, all has to have to do with these subduction settings where we have convergent or oceanic terrains being subducted, dehydration of the oceanic crust, causing the melting of the underplated mantle wedge, and then the ascension of these melts where they hopefully accumulate metals, fluids, carbonates, hydrogen sulfides, so forth, so on, and that then can be precipitated in an upper crustal setting with a porphyry deposit, and hopefully in a large tonnage situation. There's also post-collisional events that can cause porphyry copper deposition. But for the most part, what we're going to focus on is understanding the fluids that form through a ascension or magmatic setting in these porphyry copper systems. So porphyry and epithermal deposits are relatively unique in that they are primarily magmatic derived systems that come through from a lower depth. So you have a often mafic or somewhat mafic recharge event or plumbing system at depth that then comes up and accumulates into a mid to upper crustal chamber. And that has significant fluids, magmatic fluids, which are then typically pool at the cupola of your magmatic chamber and then released, and hopefully they contain, as I said before, the metals that are then precipitated into the host country rock or the source porphyry or stock batholith chamber that originated these fluids. And there's a lot of different metals, indicators, elements that we know and have observed throughout the course of exploration and drilling for these targets. And based on where at depth, pressure, temperature, pH, and original host composition of the originating magmatic chamber or the country host rock can often determine what type of features or assemblages or composition that could potentially resonate to a deposit or a vectoring towards that deposit. And this is a diagram put together by Dick Tosdell, John Dilles, and others in showing kind of the general association with these magmatic systems of where the different types of elements and compositions that form in porphyry copper gold, porphyry copper moly, or upper epithermal systems, and the transport with these various fluids, vapors, and so on and so on. So when these features react and you get a porphyry center forming, often when we're doing exploration in defining or finding the footprints, as we like to refer to the features both proximal and distal to porphyry copper deposits, there'll be various different settings or geometrical features that are dependent upon, one, the fluid origin, like where is that source fluid coming from at the part of magma at depth, what is that host rock composition, and then how well are those fluids able to transport through that media. Is it being permeable? Is there an alcatard? Is it being confined due to the overlying volcanic package, which often occurs in these settings? Or is there a sedimentary package that can be very reactive and have fluids transfer very far and form what we refer to as skarn deposits? And these features can be proximal, distal, far field, and fringe away from the sediments. And so how do we identify these fluid components that are being, that potentially host or originated the deposition of metals distally away from that deposit, or especially when it's buried under cover and we may not necessarily recognize it in our exploration setting. So some of the key methods that I'll be discussing in this talk today culminate from the work that we've done over the past 5 years in the project that was that we worked on. And there's many different avenues or methods of exploration, including the geophysical, which I'll not touch on today. But the key ones that we found worked that really well, and that I will touch on in the limited time that we have, focus primarily on the mapping and the alteration assemblages that are key to porphyry copper deposits, the physical properties, specifically with magnetic susceptibility, some of the simple techniques such as feldspar staining, as well as the spectral imaging of SWIR, hyperspectral, followed by chemistry and mineral composition. And these are all methods that we can use to identify an ore body, both hundreds of meters to several kilometers, in some cases up to 15, 20 kilometers away from the deposit. And these are all methods and means in which we're trying to identify these fluid pathways or these subtle chemical signatures left by these fluids that have originated from a host magmatic or porphyry system. So to think about the alteration assemblages of porphyry copper deposits, we have models that we've built to understand the various assemblages or mineral assemblages that often occur in porphyry copper systems. And these we refer to as specific assemblages which are related to the minerals that are present within those systems. And if you think about these formation of these key mineral components, they often form under specific conditions, which we can then use to determine at what temperature, depth, composition, acidity of the source. That again gives you an idea of how far away potentially you were from the source of the fluids. So this is a diagram that we put together for our publication from the new CIM Porphyry volume that just came out the beginning of this year, highlighting the work that has been put together for the hydrothermal assemblage system with potassium, aluminum, silica, and hydrated features, showing that at high temperatures, high acidic conditions, you usually get the formation of potassic alteration or potassium feldspar, biotites, anhydrite, tourmaline topaz, zircon sword at depth. And then under conditions of vertical ascent, you will get a fluid buffered component and generally form your more intermediate to advanced argillic alteration with clays of porphyroite, dickite, kaolinite, among other things. If you were to travel laterally in the fluid system, away towards the lateral side, you tend to get more rock buffered or meteoric fluid components, and you generally get more near neutral compositions of mineral components such as epidote, chlorite, illites, and smectites. And these can be found generally away from the deposit. And it's the key in these green rock settings is how do we identify if this originated from a mineralized system, or is it related to a more regional event, or how far away we are in that general setting. So this is a diagram that we like to use quite a bit from the pre-mining of Bajo de la Umbrera, where you can see you get this volcanic carapace in the distance. You get this lighter colored zone down towards into the valley, and then a little knob there in the center. And so what kind of zoning are you seeing in this pre-mining? And if we look at these features and go in and map them and identify the mineral assemblages that are related to each of these superficial features, then we can say that this is a typical zonal pattern of alteration from a center core, quartz, magnetite, potassium feldspar in the center, which is very resistive and forms that knob in the center, where as you get around it, you get more of this biotite, phyllic, muscovite surrounding that deposit, and then far field away from that, you go into this green rock space, which is dominated by epidote, chlorite, carbonate, among other things. And this is a very classic example of the alteration assemblage system that we've modeled at multiple different deposits throughout the world. But if you get to an area where a lot of these assemblages are absent, or they're covered, or you're only in that green footprint, what else can we use, or how else can we potentially identify which direction that we want to go towards in order to find that center of the deposit? So the key feature again is identifying these alteration assemblages. What are we looking at that's distal? What are we looking for that's proximal? And how can we identify those with, as a geologist in the field, as well as improving that in the lab or in the core shack or in the analytical work when we send it off for assays? And often when we're out in the field and we're making these observations, it's very important that we don't immediately assume that we're in a specific alteration assemblage. If you happen upon a sample that has a high amount of chloride or epidote in it, just use those terms of the minerals present in that alteration setting, because oftentimes we will kind of pigeonhole ourselves into, oh, it must be this specific alteration assemblage, and so I'm this place. Whereas sometimes you may get cases where you will find a new interpretation or a new way to observe these features, where something that's got a lot of chloride, epidote, albite in it may not necessarily be propylitic, but may be a more deeper seated sodic calcic alteration component. And when we're doing these mapping exercises or identifying exercises in going out into the field, it's identifying these key mineral features and timing of if it's in the vein fracture or fracture orientation, what is the timing of these events? As oftentimes we'll see overprint. And also in the work that we've done over the last 5 or 10 years, not just at MDRU or elsewhere, we've actually observed potassic alteration distally from the deposit. It doesn't necessarily occur within the core of a system. You can have an early high temperature potassic feature that extends kilometers, in some cases, away from the source of the system, basically priming the original host rock for then later events that come in. So we have to be very, very careful when using these terms in your exploration setting. And then identifying some of these key minerals that are clays or in some cases prehnite can be very, very difficult to identify in the field. And so using additional tools or techniques such as SWIR or hyperspectral imaging or analytical chemical analysis can improve your interpretations or understandings of what minerals are present in these systems. So again, when you're going out and doing these alteration mapping projects or out there mapping in first boots on the ground, there's some very key features that are important to collect when you're doing these projects. And that's to identify your vein and vein selvage, how many veins per meter, so to get your density, as well that gives you your alteration intensity. And then in projects when you're going to mapping, and often this will depend on budget or the amount of time you have to spend on an exploration program, is what is the resolution or the amount of sampling that you can do within a given area. And we've found in our studies, especially if you start to model and do the statistical calculations of your data sets that you're collecting, that a grid setting is much better than a transect. However, if you have a large regional area to cover, you have to make those choices, and mapping scales based on your target area can reflect that, as well as the surface outcrop availability in the areas that you're going to identify. But so in the case of the work that we've done over the past 5 years, and as part of this project that we started back in 2014, 2013, we collected a sample approximately every 250 to 500 meters and took slabs to get as much information as possible, with the assumption that when you go out into the field, you may never get back to that spot again. So you want to collect as much information as possible from a site. So each site we collected magnetic susceptibility measurements, and each site we collected vein density, structural density, and notes regarding what was observed at each site. And this is just a simple table to put up what the type of features that we expect to see in whether we're distal in an advanced argillic or propylitic setting versus proximal, potentially in your potassic zone or sodic calcic zone. But as I mentioned previously, sometimes these zones or types of alterations can be distal, and we'll go into more detail that later in this presentation. But the general consensus is that if you get closer to your phyllic or your potassic alteration, that is where you're getting into potentially more ore bearing or mineralization. So as I mentioned before, one of the key alterations is in distal is this propylitic alteration. But what we've discovered in the last few years with new mapping and new identification of these minerals related to that is that the presence of the sodic or calcium rich bearing minerals at the expense of potassium and iron. And this has been known about for some time, and is what we refer to as sodic calcic alteration, which is an assemblage primarily of albite actinolite with epidote and chlorite, plus or minus potentially titanite or garnet. And this alteration typically occurs at or below depth, where you have a connate or brinal water that's been pulled in through into the basins where these porphyries are being emplaced due to the subduction and along coastal terrains or coastal waters. And these basal brines interact and provide the salt or the sodium that then goes in and replaces the potassium bearing minerals. And generally are fracture controlled, but can be very pervasive and found throughout the district. And often has been observed as being below the system and somewhat controversial whether you're missing the upper part of the package or if you're just directly adjacent to something that's more mineralized. In the case of potassic alteration, this is where you get the addition of potassium and iron at the expense of calcium, and often this can be very observed with increased feldspar veining, biotite veining, with plus or minus magnetite or anhydrite, but you can also get epidote in these systems as well. And there's been a lot of work done on mineral chemistry in the epidote space or epidote chlorite in identifying where in these indicator minerals you're at, and the composition of your epidotes in a potassic setting is much different than in a sodic or a propylitic setting. And there's quite a bit of work that's been done in the last few years, specifically at the codes and others with Imperial College, and as well as work that we're doing. And it's not something that I'll address in detail in this talk, but I encourage you to go out and look into this setting, because there is some very unique work that's coming out in this type of exploration mineral indicator observations. And then we get into propylitic alteration, where you get more of the oxygen or carbonates, sulfur, and water into these settings where you get more of a hydrous mineral assemblage, often dominated by epidote, depending on temperature and depth of these fluids as they extend outwards. And the amount of carbonate or oxidation state of these fluids as you move outwards can provide opportunities for hematite dusting or hematitic reddish zoning around these porphyritic halos. And oftentimes we'll draw just this nice little rounded feature of porphyritic alteration in the overlying package. But again, this fluid system is often confined by the aquifer or the groundwater table and can be dependent upon the permeability or porosity of these fluids that are traveling into the outlying country rock. And this can have very patchy alteration, or you can get very pervasive or very strongly fracture controlled, dependent upon the host rock. And if you get a case where you get a lot of veining or vein density, that can be used as a indicator of direction or orientation if you can have a good understanding of your tectonic system in the area of interest, and reconstruction for potential vectoring and sourcing back to the source of these fluids or fracture control systems. But it can also be very difficult to identify that, because in the case where it is very patchy or the veining vein density is very low, it can be very tricky to say, well, is this related to a magmatic system, or is it a porphyry magmatic system, or is it just something that's not related to an area of interest? Excuse me. And the other alteration is a philic or Serocytic alteration, or an SEC is we can break it down further, which is the primary addition of it's a hydrolytic alteration assemblage where you get the formation of muscovite. If it's very fine grained, often we'll refer to that as sericite, plus the main ore bearing, typically the main ore bearing mineralization. But these are generally confined to the few hundred meters or up to a kilometer around the main source of the ore body. So the next slides that I'll present are based on the work that we did with the N-Circinic Footprints project. So just a brief overview, this was a multi-scale collaborative project that was conducted in Canada, along with a copper site and a gold site and a uranium site. And the work that we did was focused primarily on the copper site, which is the Highland Valley Porphyry Copper Deposit located in south central British Columbia. It's a large scale deposit made up of at least four mined targets. That is a very large deposit that's been truncated and cut by multiple structural features. And the main cupola it's formed in the Gishon Creek batholith, which is a concentrically zoned batholith mafic on the outer edges, which grades inward to a more felsic quartz monzonite central part of the deposit, from which the main mineralization was placed in more of a stock setting as opposed to the individual porphyry deposits. And as part of this project, myself and our students went out and sampled over 1,000 samples, which we had detailed field mapping and structural modeling, petrophysical properties for all these samples, outcrop magnetic susceptibility, Feldspar staining on these images, multiple element 4-acid analysis, as well as mineral chemical analysis and isotopic composition. And we did a joint collaboration with the Geological Survey of Canada and the BC Geological Survey, looking at till, which is glacial till in Canada. We have a large component of glaciation during the past glacial period in Lake Wisconsin, which deeply incised and eroded the upper part of the porphyry system and covered the entire area with a few meters to upwards of 300 meters of glacial till moraines and so forth and so on. And so this project culminated in multiple manuscripts, theses, and reports that have come out in the last few months, in the last few years. And I strongly encourage you to go to our website where you can see the results of this. So one of the key things is that when you're going out and doing an exploration program, often we try and collect as much information and much data as possible. And we did a lot of work with magnetic susceptibility measurements, which is simply collecting to see the amount of magnetism within that sample. And oftentimes when we're doing exploration, we collect this data, but it generally often will just sit and not really be utilized to its full potential. And as part of this project, our students went out and took measurements at each outcrop where a sample was taken, as well as doing a more detailed analysis on the hand sample, as well as sending it into a lab, a petrophysical lab, to collect additional information. But one of the results from this which is published in 2019 by our student Kevin Byrne and our other co-authors, is looking at the variation and results of these outcrop measurements. So at each site, the student and their field assistant would take 10 measurements randomly along the outcrop, and looking at the results from each of those measurements to tie into, can we determine the intensity of alteration from these magnetic susceptibility measurements and correlate that to potential vectoring and this the distal orientation that we did across our grid sampling technique. So when we look at the term that we applied to this coefficient of variation, or what was the variance between these analyses along each outcrop compared to what the magnetic susceptibility, the mean magnetic susceptibility measurements of that outcrop, you can plot that up. And what we observed is that you could use that variance, like how much, if it was all the same value that we were collecting from that outcrop, or there's a high degree of different values that were coming back. And you could quickly see that there was a correlation between those zones that were unaltered, that had no variation, or between those that had a slight change in mean magnetic susceptibility, but a high degree of variable results that came in, which indicated a lot of alteration features. And so this proved to be very important, because in zones of intense alteration, where you have a high amount of fluid components that moved in, a lot of fractures, a lot of alteration that's gone in and been mag destructive, you can quickly discriminate between zones that are very small or narrow, such as an isolated copper occurrence, versus a porphyry center where hopefully those fluids travel to a much larger distance or a much larger footprint, versus something that's more a regional alteration zone. And so you can quickly discriminate in an area of field mapping where you're at in the system. Are you located towards a intensely altered zone, anomalous response of intense alteration based on these coefficient variations and your magnetic susceptibility measurements? And plotting all this up, we could discriminate and identify features and vectors related to this magnetic composition up to 5 kilometers away, directly related to the porphyry, the main porphyry mineralization located in the center of the deposit at the Highland Valley mine, which is currently being mined. And the key thing was is that we could, because Highland Valley, the Gishon Creek batholith, in which the Highland Valley is the, the the Gishon Creek plays main the host. The magnetic concentration is much higher distally due to the rocks being more mafic and diuretic compared to the center, which you can see in this center diagram here, with the outcrop susceptibility measurements are much higher on the periphery or on the edges of the batholith compared to the center of the system. But when you start plotting up these coefficient of variation values that we get from these measurements, the center of the system pops out right away, and you can identify where those alteration intensive zones are. And it also gives you an idea of potential size of your system, where you're located. One of the other things that we did as part of this project was doing Feldspar Stain, which has been used for a very long time, using sodium coltan nitrate and emerith to identify and stain potassium-bearing minerals as well as calcic feldspar. And it's a very simple technique, but extremely useful in identifying these high temperature potassium bearing minerals, which are potentially related to a mineralized system. And with the new imaging software that's available, and often freely available, that you can get, these are results using the ImageJ program. You can take images of these feldspar stainings and extract out the minerals that are potassium bearing as well as the plagioclase bearing, and quickly use that to correlate to the vein structure or the ellipses or the early potassic veining related to this, and quantify that, and then plot it up and identify zones of potential potassic or related to potassic alteration. And this is work that was done by our student Guillaume Lesage, who just graduated or defended successfully last year, and is a very, very detailed and very unique work that he pulled together in order to identify this new alteration mapping that hadn't previously recognized this distal potassic component. And this is in some cases related to small isolated pockets, but in other cases it's related to this distal fluid, high temperature fluid flow along pre and syn mineral structural tectonic setting at the time of these porphyry copper deposits formations, and basically primed the area for the eventual main deposition of mineralization at the Highland Valley and Lornex and Highmont deposits. So a very, very simple technique that can be used to identify very key mineralogy or mineral assemblages in the exploration setting. And here's some quick examples to show that if you have a rock like this, you can see there's clearly veining in here, and you can say that it is potentially potassium feldspar, but with the stain side, you can quickly see these conjugate sets of potassium feldspar veins related to the high temperature system. Whereas something like this is the complete absence or removal of potassium bearing feldspar, which is part of the sodic calcic alteration that's observed at in the Gishon Creek batholith, versus something that's propylitic, where you get these selvages and halos of potassium and calcium destruction, but you can still see primary K-spar in the edges of this system. So very, very useful technique to use, and can be done on a few samples just to train your geologists into what to observe in some of these settings. And that's kind of the key point is as you're going into using these different techniques, is to train your geos in the identification or identifying the key mineral assemblages in these proximal versus distal alteration types. And one of the other ways one of the techniques or methods that we use is shortwave infrared spectroscopy. We use a halo or teraspec machine here at MDRU, and it's a method by which we can identify the ALOH bonds in those hydrous minerals that have these reflectance or wavelength features that have been characterized. And there are numerous libraries out there that can provide the service and understanding. But the basic sense is that these clays, ferrosilicates that are present in advanced argillic settings, intermediate argillic, or distally away from your deposit in porphyritic settings, have specific elemental signatures or wavelength signatures related to specific mineral composition. And we can identify those key minerals such as muscovite, which has a very distinct wavelength feature, 2200 feature, which can be used depending upon where that wavelength falls or how wide that trough or feature in that analytical result from your analysis can be used to determine the crystallinity and in some cases the composition of that sample, which is dependent upon the hydrothermal fluid from which that mineral crystallized in both composition, temperature, and pH. And plotting up that data can quickly give you an idea of where you're at in your system. Are you in a more intermediate, moderate temperature, or higher temperature between your phengitic sericite composition versus another? And this was done by Guillaume Lesage in his PhD dissertation, where he characterized the teraspec along with work that was done at the lab on Vancouver Island, comparing these features, the LOH features and white mica composition in distribution and improving our alteration map that we did in the area. Another one of the things that we did and has been discussed in detail, especially with the companies such as CoreScan and TerraCore and others that have come up recently, is the use of hyperspectral imaging. And this is I won't go into detail about all the specifics of the method and technique, but this is another way to scan or image your samples, often done on your core, to identify, again, these key spectral related minerals such as white mica, sericite, illite, and smectites, clays, kaolinites, and so forth and so on, using this known wavelength features. And we conducted this study not just on the drill core that's provided through the company. In this case, CoreScan provided the analytical work for us on our future site, but we used the same technique on individual cores or individual slabs sampled from our deposit. So the samples that we not just did the feldspar staining on, but we would take the backside of that and sent that in to the University of Alberta with Benoit Rivard, Professor Benoit Rivard, and his student Philippe Lepezewski, who then analyzed these samples with the hyperspectral imaging. And we were able to identify and pull out the composition, the chemistry of our white micas, our epidotes, our chlorites, and correlate that with grain size as well as the alterated assemblages, and using it to vector towards our potential deposit. In this case, we knew where it is, but we could build in and identify key features. And one of the unique things about this technique and this method is that in the upper right corner, you can see this sample of epidote veining. There's two separate epidote veins are here, which we had assumed had occurred at the same time. But when we did the hyperspectral imaging and got the composition back from that, it turns out there were two completely separate veins that had formed at a separate time, and one correlated to mineralization and one was related to another event. And this was a very unique and rapid way, so we started to follow up more on that and identify which relationships to these specific veins that we could then use to out in the field with our other samples. And it was a very interesting and unique setting to quickly identify which features we should look for that are related to mineralization and which features were not. And this was just recently published in Minerals this past year. And so this is another unique way that you can then train your geos when you're in the field or in your core shack or collecting samples, is that it's not necessarily you have to do it on every single sample that you collect, but you can do it on representative samples in order to better train your geologist into identifying or understanding the minerals that are present within these specific veins or vein selvages or alteration and halos that you can then use and go back when you're going out and continuing mapping. One of the key minerals that was observed doing this process was prehnite, which has often been associated with a metamorphic or regional event. But during our exploration and using these techniques, we discovered that it was actually related to the mineralization due to the composition of these units, and had never been previously recognized as a alteration, a distal propylitic alteration feature in these type of settings. Which was very useful, and the students can now go out and identify prehnite in the field, which is very, very useful and unique. But we didn't just do this on rock slabs and the core, we also applied it to our surficial material that we had collected. And in a lot of settings where you have cover or potential gravels, glacial tills, stream sediments, sands, wherever you're at located, the use of hyperspectral imaging over this cover material can quickly identify key minerals of interest. In this case, phengitic mica pops up, and you can quantify the presence or visual reflectance of these minerals. And at each of your site, when you start plotting that up, it will, if you're closer to the sample or potential target, you will have an increase in these potential minerals. And in the case at Highland Valley, we were able to clearly show from our distal collected surficial material had more of the distal propylitic minerals related to it, in this case prehnite, whereas our proximal till that we collected directly over the deposit or slightly down from the deposit had much more high occurrence of minerals that are potentially related to the center or the narrow argillic alteration related to the structural features in the center of the system, which is a very, very powerful tool which you can then start mapping and use to quickly identify where you're at in the system. And oftentimes when we're doing or preparing our till or stream sediments or gravels or sands for heavy mineral separation, we may lose these lighter clays or lighter elements and not necessarily get them in recoveries or used in a analytical technique. You may see it in an algorithm or whatever analytical package you're doing over your surficial material, but this is if you take this before the separation or the preparation is done, and you can definitely determine that there is absence or presence of these specific minerals of interest. So looking at a lithochemistry in porphyry copper deposits. There's been numerous reports and studies that have been done throughout the history, and I strongly encourage you to look at or read Scott Halley's paper that he just came out with and has given numerous talks over the last couple of months on, and it's an excellent report. This is a image that was put together by the late Peter Winterburn, kind of showing the chemical distribution or chemical halos that often occur around porphyry copper deposits. And we tend to see both a lateral and a vertical distribution of these key elements of interest, which are related to the alteration assemblages that occur both vertically or laterally, vertically in the upper part of the system, telescoping down to the center of the system, versus what you see laterally. And this is related to the clays that then form near the upper part of the system or in the upper part of the system, versus distally where you get chlorides, epidotes, and so on, or the precipitation of metals or key elements such as bornite chalcopyrite in the core of the system, which is very copper rich, versus salari or galena, which precipitate at much different conditions distally away from the deposit, where you get more lead, zinc, cadmium, manganese, bismuth, vanadium as a alternative to the composition that you're looking for. Above, these tend to form nice chemical halos, but if you're dealing with a transected or truncated deposit, these can be variable. But the key component in all of this, because the minerals the metals of interest are chalcophil and tend to form with sulfur, most porphyry copper epithermal or mineralization deposits in general tend to be anomalous sulfur deposits. So sulfur can be a very key element of interest when you're doing exploration, in that it is the primary element that binds with your metals of interest to form the metals that we can use for exploration. But again, sodium, calcium dominant at the base or the side of the system due to your soda-calcium alteration, high potassium in the core, and upwards above to more copper, moly, gold, silver, and you looking at your gold to copper ratios or zinc to copper ratios, zinc to silver ratios are very, very useful tools or useful techniques in order to identify potential halos around your system. One of the things that we've done at MDRU with the work done by my colleague Farhad Bouzari is using this known understanding of these different elements that occur in porphyry deposits, both vertically or distally. He put together a porphyry index based on the analytical results that you get from these multi-element suites, typically fluorescent, but can be applied to other techniques. But looking at copper, moly, tungsten, and tin versus antimony, tellurium, silver, arsenic, and lithium, which tend to form at the upper part of the system versus lower part of the system. And he was able to show and identify that using this system, you can identify, in this case, this is located in central British Columbia, that the index related directly to porphyry copper deposition in the center of the system at this deposit. And then as you move out distally away, it becomes more into background or less likely indication. So again, this is using the understanding of the mineral composition, the minerals that form up your alteration assemblages, and what key elements occur in those settings. So able to identify anomalous samples, reflecting this enrichment or depletion of elements of interest. And in this case, the key elements of interest for porphyry copper deposits are copper and moly, tin, tungsten, antimony, tellurium, and lead. And there are others that you can potentially use into these type of indices as well. Fertility diagrams are another key component of use of elemental composition in porphyry copper determination. These are diagrams that are championed by the late Jeremy Richards and others, and it highlights the fact that porphyry copper deposits typically are highly oxidized or highly water rich. And because of this, the term atachitic or magma fluid rich like rocks will have a significant chemical difference compared to those rocks types that are quote unquote dry or less likely to have be related to porphyry copper mineralization. And so these water-rich magmas generally suppress plagioclase fractionation, will generally have depleted middle rare earth elements or heavy rare earth elements and increased strontium, yttrium, and high field strength elements. And you can put together diagrams. In this case, one of the key ones that we often use is strontium yttrium over versus yttrium or lanthanum and terbium. And in Highland Valley, we see that same trend where you have the early outer part of the deposit related to the border phase or the Gishon Creek variety, which are the distal parts of the Gishon Creek batholith and the Hyde system are generally lower, and it's trending to more fluid or increased fluid bearing rocks of the central part of the system, which are related to the and host the mineralization of the main porphyry copper deposit. And the application of this method is can be used on rocks, not just in the whole rock setting, but also can be applied to the mineral setting. In often we use zircon or apatite as some of the key indicator minerals in porphyry copper deposits, and I'll focus on that in the next few slides. But the key thing about this is to apply it to fresh as possible, because often in the case of alteration, you'll get the change or the signature of particularly strontium with the removal of plagioclase and potassium feldspar. You'll get skewed results. So when you're going out and sampling, you want to look for as fresh a sample as possible. So correlating what you get in your fresh samples to what you would get from your alteration samples, you can then normalize that chemistry in order to identify the key anomalous variants in your sampling suite. So the host lithology may not be the same across your entire district, and so it's important to understand what is the original or background composition that you have in your area of interest, and correlate that to alter samples. So because oftentimes when we're going out and doing our field mapping and sample collections, we as exploration geologists tend to focus in and go for the samples that have the veins or have the metals, and we don't tend to sample rocks that are barren, which we need to get away from, because it's very important in order to classify and correlate and understand where you're at in the system. You need to have that background value that you can then put into your model or your if you do machine learning or anything like that, so that you have a value to compare back to and understand why it is that you are anomalous. So again, not just taking or high grading your system, but identifying the differences between what the rock originally looked like, can provide the understanding for these subtle chemical differences in your analysis. And so the students would take that and compare the composition of the fresh rock or the whole rock to those of known alteration samples, and you can see the change as you move away from the center of the system towards background composition in not just the the original host rock, but the center of the system to the distal part of the system, and you can see elevated or depleted zones of minerals or elements of interest. And so this is a very, very useful technique when you're wanting to normalize or compare rocks across your entire district, and you have multiple different units that you're using. So it's very important to normalize your altered sample to the original host rock composition if you can identify that. One of the key ways of doing that is, again, using different modeling and ratios. In this case, this is a Pierce element ratio diagram that we just recently, that our student Kevin Byrne just recently published in this SEG special publication last year, the Green Rock special publication, looking at the addition of mineralization towards more muscovitic or chlorite and kaolinite composition based on the original, what you would expect to see along your control line of normalized rock types in the Gishon Creek batholith. So again, a very useful technique in order to understand what are the additions and depletions in a setting of porphyry copper alteration. And there's lots of different programs and softwares that do this. We tend to use IOGAS. It's a very useful and has these built in. But there are other programs out there and that you can use and utilize this technique. But again, it's trying to identify the key elemental components and to identify whether there is an anomalous feature related to that, and being very careful in understanding what it is you're actually looking for. In case you take a sample that has a high amount of iron or magnesium, and you look at another sample that has very low, but when you go out and actually look at the rock, one happens to be a basalt and the other happens to be a monzonite, obviously one is going to have more than the other. So it's very important to tie everything back to the original host rock and not just take the chemistry for granted and dump it into a model. You need to have that correlation between your original host lithology and petrography. So it's very, very important to maintain a good workflow with your sampling procedures to understand what the host rock is, what the petrography is, what the alteration mineralogy is, and then apply your chemistry to that. And you can use your chemistry to help identify the key minerals, such as in this case. And when you plot that up, as Kevin has done, you can quickly identify zones or areas of interest based on the composition and the mineralogy throughout the entire district. So again, this is important for your workflow. So your rock chemistry or your rock mineralogy. So combining your field mapping, your staining, your spectral data to define that alteration assemblage and their domains through time, and identifying these overlapping anomalies and gradients. So sampling, petrography, lithochemistry, and normalizing towards your original host rock. So the last few slides that will go into this presentation is the work that we've done looking at indicator minerals in porphyry copper deposits or epithermal systems. And these indicator minerals are very key to the whole fertility aspect of porphyry copper deposits. And so there are several key factors that we use in order to determine whether an element is a key indicator, such as oxidation state, temperature of the forms, pressure, water, metal, chlorine, sulfur in the case of apatites. And there's lots of different minerals and key minerals that have gone into the research in the last 10 to 20 years. But we're going to focus primarily on zircon. I've just recently published several manuscripts on this and did quite a bit of work on zircon composition at El Salvador for my PhD. But these are minerals that tend to be resistate, that survive transport, and can be used to identify the composition of the host rock during the formation history of its time. And zircon is one of the unique minerals that can do this, in that it is very robust and resistant, and doesn't break down as soon as it forms and crystallizes. It also preferentially incorporates uranium as opposed to leadensite, so it's often been used as a geochronological tool. You can have fractionation with the hafnium isotopes in the sample, and identifying the oxidation and fluid state with the rare earth composition of europium and cerium in its chemical structure. And from the work that we've done over the past decade or so of myself and others, we've identified key chemical composition features that we can relate to porphyry copper deposits versus those that are barren or unmineralized. And at Highland Valley, this is work from the paper that was just published in Mineral M Deposita. We looked at the zircon composition of samples from the distal edge of the batholith all the way down into the core of the system to post-mineral dikes. And in this diagram here to the right, you can see that the europium anomaly, or what we use to determine whether it's an oxidized or fluid-rich magma from which that zircon crystallized, is generally low for those that are pre-mineral and distal, and increases over time. This is a diagram done by age of the sample, and it culminates at the top here with the unit. This is where mineralization occurred, and it drops off rapidly with the late to sin minerals, intrusions related to the salt and paper and post-mineral diking. So this is very useful technique to say that I'm outside of the system distally from the deposit based on the composition of these zircons, compared to the center of the system, where this is more fluid rich, more capable of producing a large scale porphyry copper deposit. And so we then applied that to our detrital setting. Can we take that information and look at samples that we've collected in these glacial tills? And this is work that was just published in the SEG Scientific Communications, and it's open access, so it's readily available for anyone who's interested to take a look at the results. And we went out and collected glacial moraine samples, both up ice, above ice from, or up ice from the deposit, directly over the deposit, and down ice and lateral from the deposit. And based on the results, we could clearly see that up ice and down ice and lateral have these low values, whereas above ice and directly down ice from the deposits have the more elevated values. And this we interpret to be a direct way to fingerprint the bedrock sampling and correlate that, yes, we're in an area that is of interest for the potential formation of the porphyry copper deposit system, in this case, Valley. But it's very, very useful technique looking at the trace element composition within these samples to define a terrain of interest, or large scale terrain map using these detrital chemical signatures. So not just looking at a provenance scale or where the source of these samples are, but looking at it as a potential means to quickly evaluate whether we want to be in this catchment basin or in this area versus areas of non-interest in some other way. And we're currently working on additional studies in epidote and apatite that hopefully will be coming out in the next few months or next year. So in summary, field mapping and measurements, make sure when you're going on the field to collect as much information as possible. You want to identify your petrography, what is the original host rock, collect all kinds of structural vein orientation compositions. Density is a very useful technique, just identifying what is your vein density to plot that up on maps, and that can be a very simple and useful technique to identify how far away you are potentially from a source. The magnetic susceptibility, collect measurements on your outcrop, not just the sample that you're collecting. This is a very, very useful technique for alteration intensity. Spectroscopy and SWIR and hyperspectral imaging and lithochemistry, again, collecting as much information with the understanding that you may not ever get back to that outcrop in question. And oftentimes, unless there's a mineral of interest, we don't. So it's very important, because these distal alteration assemblages are very key to knowing where you're at in the system. So it's getting away from that, looking for the big key feature. You want to understand what it is in these distal alteration compositions, and that's doing due diligence on your petrography, staining, again, combining all of this data with your field observations to characterize these alteration assemblages and timing of these events. What veins are cross-cutting? What's within these veins? Is there carbonate present? Is it all epidote? Is it all albite? Is it all potassium feldspar? And so the overall copper alteration, this is a simplified model of alteration assemblages in North America that we just published in the Xeon Porphyry volume. Again, identifying where you're at in the system, both above or below. Can we identify which elements are present in the sodic, potassic, serocytic, and propylitic? And in general, the key vectors that we found to be extremely useful in this type of setting for distal to proximal in porphyry copper settings are identifying where you're at in your alteration assemblage, high temperature, low temperature. But again, bear in mind that you can have small zones or small pockets or distal pockets of high temperature alteration. Magnetic variance, normalized lithochemistry, mineral composition anomalies, as well as surface soil and mineral indicators. So with that, I will end, and sorry I went a little bit over time, but hopefully we have an opportunity for questions if there are any.
Thank you so much, Dr. Lee. It was an outstanding presentation. It was terrific. So yeah, we have already some questions. So here from Aristide. In Greenstone Belt, it is sometimes difficult to make the difference between green schist facies metamorphism and propylitic alteration. What key can we use to make this difference?
That's a very very good question. There, oftentimes in what we observed and what we used to differentiate between prehnite that was related to mineralization versus, well, related to fluids that potentially came off mineralization versus the regional component, was if they were in the vein. At Highland Valley or in the Gishon Creek batholith, you did observe prehnite in within the ground mass of the rock, pervasive prehnite, which had a slightly different composition, different textural control, but for the most part, we identified that as being part of the regional component, whereas these veins that were dominantly prehnite or prehnite chlorite or prehnite chlorite illite were coming from the source. And it can be very difficult, and I acknowledge that it can be quite hard to say whether it is or not. Kevin Byrne, just his publication on sodic calcic alteration in the Highland Valley deposit, that was in another paper in the new SEG Green Rock volume, addresses this, and he goes into more detail in the discussion of the presence of prehnite and tourmaline in these distal propylitic and sodic calcic alteration. And if you want to learn more about that would be a good source to go to for understanding why we made the determination that prehnite was related to these distal fluids from the center of the system. For your case, I can't go into detail as to what would be the best way to look at yours, but it's again identifying what is the textural relationships in your samples for where you observe the pre-night, and if you can use that as a way to potentially identify if it's related to a regional versus hydrothermal footprint.
Great. Anderson said, in Brazil, we have some example of porphyry deposit formed during the Proterozoic that are deformed and metamorphosed in amphibolife. Do you think we can use porphyry indicator minerals and or porphyry vectoring and fertility tools to identify potential for porphyry style mineralization in this case?
That's a very good question. There's very few, there's not a lot of work that's been done in those age rocks or that type of formation. There has been some work done on Archean rocks in the indicator space. Lou et al. Just 2-3 years ago published work on Archean systems in Southeast Asia and China. But it's just a matter of analyzing those. If you can get the indicator minerals such as zircon or apatite, in that case, they may have to use, since they are like amphibolife faces, you may need to look at potentially apple or garnet if it's present, or titanite may be another indicator mineral of use, and seeing if there is differences in the composition between those versus something that may be in background. But the Archean paper by Lou might be a first step to look at and compare with your samples versus what been observed in other places.
Great. Dina asks, how were the coefficients defined for individual elements in the porphyry index?
So Farhad based that on work that had been done in detail in that area, and the knowledge of where these specific elements are used, or where these elements occur within the system, whether it's vertical or above the typical porphyry copper deposits versus at depth. These were just the ones that he happened to use and worked very well for that specific setting. He has applied other elements and put that in the index. We are applying it to other sites and other deposits, particularly in our work in Colombia, and a bit of our work that we've done in the Western Tethyan Belt as part of our Western Tethyan collaboration. But it may not always work for that particular area that you're working at, and it's just something that you kind of have to play with. And what Farhad did, which was very useful, is that he used those values and normalized it into a value that you could barely use, because oftentimes you'll have very low tungsten values versus high copper values, and so he used that index to kind of normalize everything together in order to correlate it to that specific zone. But yeah, there is opportunities there to add or take out some elements, and he's done a lot of work on that, and there's going to be some new studies coming out in regards to that. But it's based on the fact that in these systems you get specific mineral composition that occurs, and those minerals generally contain the high amounts of the specific elements of interest, such as arsenic, antimony, silver, and so forth and so on, above deposit versus copper and moly at depth.
Juan Antonio Verástegui asks, what kind of vectors can be used to differentiate a porphyry copper deposit from a porphyry copper deposit related to skarn copper?
I haven't done a lot of work in the skarn setting. That's so in high carbonate settings or sedimentary basin settings, often what is very useful in those settings is looking at the carbon or carbonate. Carbonate isotopes have been shown to be very useful in those kind of settings where you can vector from the high temperature source away from the system. So our new director that we have at MDRU, Sean Barker, has done a lot of work on this, and we have quite a bit of students who've done some work in these settings looking at these carbon isotopes. And we did that a little bit at Highland Valley, and Kevin Byrne has published on that. We did some work. We had a student who did work on looking at the UV reflectance of these carbonate veins in these type of settings, and you can use that to show the reflectance of the ultraviolet light of these different veins will be reflective of where they were sourced, and oftentimes you can see that they are higher temperature veins related to mineralization. But these are carbonate hosted or some skarn deposits, and I can't go into detail and all that. That's work that's done by the students and just it's come out in some recent theses. Chemistry-wise, you're wanting to look at potassium carbonates, the garnet composition. There's going to be a lot of accessory elements that are related to these deposits, and there's been a lot of work done by Larry Meinert and Audi and others on that. So those would be the first places I would go to. But from the work that we've done, the carbon isotopes seem to work very well.
Abu Kafi asks, could we use portable X-ray fluorescence data instead of ICP for geochemistry analysis, such as fertility or porphyry proximity index?
Yep, so there's been a lot of work recently. A couple of publications have come out recently in looking at specifically using portable XRF data, and the latest models are more user-friendly and more, they're all Bluetooth capable now, so you can get real-time values. They're not quite there yet for getting the information into a more something that you're going to put onto your like a 43101 or you really do need that lab certification to say for quantification of your data analysis in QA/QC. But with the new research that's being done and the improvement to the technology, it's getting more and more beneficial in getting like real-time data while you're out in the field, and taking that data and quickly plotting it into a GIS setting onto your portable tablet or back into the core shack or the office if you can send it back to the office in real time to get a generalized idea of where if you're seeing an enrichment or depletion of elements of interest and following that up or chasing that up, the drainage or the outcrop or whatever. So yeah, you can definitely see the improvements to that technology. And I didn't discuss that in this presentation, but we've also started doing a lot of work with the companies that are producing these units, such as like the SciAps or Reflex. They are doing a lot of work with universities in this specific research and looking at like a LIBS unit, which is a handheld laser system for looking at trace element composition. So we're trying to do more work and research in that respect and providing a unit that can be used in the core shack or out in the field to get these chemical evaluations, not just on whole rock setting, but on a vein or individual alloy.
Leffer said, in successful distinguishing hydrothermal prehnite versus metamorphic prehnite, as you said, it is possible also to distinguish metamorphic epidot actinolite versus hydrothermal epidot actinolite in a green schist environment with porphyry overprint. What are the key distinguishing factors, halos, vein salvage, or association of certain minerals? Thanks.
Yeah, so there is I really encourage you to look at that new SEG 2020 volume, because they go into details on the composition of epidotes, chlorites, and other key distal minerals related to porphyries, epithermal deposits, whatever. Excuse me, but there are key elements like antimony, galenium. There's a whole suite of key elements in epidote that can be potentially related to a hydrothermal fluid versus a metamorphic fluid, and that's often done like the chlorite proximeter, looking at like titanium concentration and other key features to correlate to the temperature of formation. But it's quickly identifying, and you have to use very specific analytical equipment in order to get that information, typically a laser ablation ICP-MS setup, which some commercial laboratories are starting to move towards and doing that. But oftentimes you have to send that to a university lab in order to get that information in composition. Texturally wise, we observed in Highland Valley with our chlorite and our epidote, again, looking at that hyperspectral image that I showed earlier for those epidotes, the key composition, and I can't exactly recall what that was. I'd have to pull up the manuscript again, but there was a clear distinction between that epidote that had the high coloration or high spectral image versus the other one. So that one was related to an earlier higher temperature event related to mineralization, and the other was a much later, probably still related. It's a cooling event of that fluid as it was passing through that same rock. But it's identifying these key features in the mineral assemblage, which oftentimes it's very, very difficult to see that visually or with a hand lens or under a petrographic microscope. So you oftentimes do have to go that further step in using a spectral feature or a more analytical approach. But it's still important to identify what minerals are within that vein and getting the timing on those veins as much as you can.
Great, we have a couple more questions. John Sarong asks, was the porphyry index used in other mining districts, maybe in South America?
So as I mentioned, most of the work that Farhead and our group have done in MDRU has been focused primarily in British Columbia, but we have been approached, and Farhead has been attempting to use this technique at other locations. I can't speak directly for other companies, but I know companies have been using it and have been very interested in our reports that have been presented by Bazor and others in our group. So there is opportunity, and if there's any interest, I strongly encourage you to check out our website and contact us directly, and we can follow up with that or give you more detailed description of how it works and what key elements may be useful in your specific location as opposed to what we've observed here in British Columbia.
Great. Our last question will be, how could we differentiate between low pyrrhotite, chalcopyrite, arsenopyrite rich, intermediate sulfidation, bornite, magnetite, chalcopyrite, molybdenite rich, and high sulfidation porphyry system using some of the techniques you have presented?
So that gets into the original host composition of the fluids, right? And that is often due to the oxidation state or the original fluid composition of the magmatic fluid as it's coming in, and that's where you get your intermediate or MSS sulfide solution in these systems. And it's a I mean, you can see it looking at reflected light petrography in these veins with the formation and growth zoning of the sulfides. But to answer your question, can we apply it chemically? They're looking at the various oxidation state in your magma, your iron composition, or using other oxybarometers such as zircon, amphibole, titanates can potentially be useful in that. And I'm not a complete expert in that specific style of mineralization or minerally. My expertise tends towards more of the mineral composition, such as zircon and apatite. And there's lots of researchers and studies out there who could provide a much better answer than I could to that question. But using like on your question to the zircon chemistry, looking at uranium titanium ratios or antimony ytterbium, yeah, you can. So I prefer to use gadolinium ytterbium in zircon composition. Others may use deuterium yttrium. Hafnium yttrium is a very good ratio that can be used in order to clarify or identify where you're at potentially with composition. In this case, what is the source? Is it a more felsic source versus something that's more mafic? Yttrium within zircon tends to be much more enriched in felsic rocks as opposed to more mafic rocks. And the same with the amount of uranium that's present in the sample. Titanium, we often use titanium for the temperature, but it does occur at a very low concentration in zircon, so you have to be very, very careful with what your detection limits are and evaluation of the titanium concentration. So we do use it for temperatures, but I because it's such a large error, I look at more of the titanium as on the whole as opposed to individual ratios, and I don't necessarily use titanium in other aspects of where you're at in what it's related to as far as composition or porphyry fertility metrics as it were. I look mostly at the hafnium, yttrium, moderate europium anomalies in ytterbium gadolinium ratios, and thorium uranium ratios.
Great. So I think that's all for today. Thank you, Dr. Lee, for this great presentation, and we hope to have you in all webinar in the next month. Thank you, everyone, for joining us today.
Thank you. And if you have any questions, I'd strongly encourage you to reach out to us. We're always willing to sit down and chat with any potential interest from the studies that we've produced over the 30 years that we've been an active research unit.
Great. Thank you so much, Dr. Lee.
Thank you. And stay safe, everyone. Take care.
You too. Take care.